record. Testing. Yes, it works. Okay. So the first thing we're going to do is we're going to take attendance by answering this question on your phones. Surely it will come up. There it is. There we go. Go ahead and take your phones out and scan that. We'll take attendance that way. So far, there's been 2 responses. Remember that I harped on this a lot when we talked about it. $14 responses so far. How many people are in here? 5, 11. 17, 22. So there should be 22 responses. Let me make sure I got that right here. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yes, 20. Oh, yes, 22 responses. Wonderful. All right, let's see how everybody responded. Again, I must commend you for coming to class on a Friday. I mean, a Friday at 5. I wish it were a Friday at 5 o'clock in the evening. You should be commended for that. All right, these are the answers so far. The vast majority of you said. There we go. The vast majority of you said B, which is the British system. That is correct. Recall that I said that it's so funny that the British use the metric system now, right? But we still use the British system. It's a little crazy, right? It's a little crazy. Don't worry, I won't make you discuss that. That's one of those things that, I thought you already knew. So, but that's okay. Make sure you know it for the exam, okay? Make sure you know it for the exam. All right. So let's get started on some work here, right? Some stuff that we need to know. We're going to do practice with math and some more solving problems, because the upcoming chapters, like I was telling you, are going to be a lot of equations, and you're going to have to solve for things. And when we were in a lab on Monday, it turned out that I needed to do a little bit more work on that. So the first thing we're going to talk about today is measured numbers. Okay, when you look at this little ruler up here I have, along with this little piece of wood, when I measured this here, it looks like it's 4.5 inches, right? But the thing is, if I were to go even, this piece of wood here is actually the exact same length as that piece of wood. If I go down, 4.5 inches, 4.5 centimeters, right? If I look at this one right here, it actually has more tick marks in it than this one up here does, right? It's actually between the half point and the next tick mark, right? So really, that piece of wood is not 4.5 centimeters, it's 4.55 centimeters, right? At least that's what we think, because even then you could get even smaller in there, right? And see how much closer that is to one side or the other. But as far as we can tell right now, it literally is just right there between those two smallest tick marks, and it looks like 4.55. So the point of this picture is to demonstrate to you that there's a certain amount of uncertainty for when you measure things. Okay, measured numbers have uncertainty on it, and you can take an entire semester class just on uncertainty. Right? When you become a forensic scientist, one of the things that you have to learn is how to do what they call propagation of uncertainty, which is determining how uncertain any kind of measurement is. Right? And so it's it's a whole semester-long class. So any of you guys want to do that with your life, right? Be prepared for doing a lot of statistics. So when you're talking about measured numbers, the way that you know that you can rely on these numbers, right, is based on its significant figures. The significant figures are the part of the number that are not disputed, right? The rest of the number, right, is the part that is like, uncertain. Okay? So there are several rules, right, for significant figures. The first one is that any not zero number, right, is significant. So how many significant figures do we have in 4.5 grams? Hello? Hello? How many significant figures do we have in 4.5 grams? 2, exactly, right? This one has 2 significant figures. What about 122.35 meters? 5, exactly. Right? So that's for that rule right there. Any not zero number is significant. Now, the next rule is any zeros between non-zero digits is also significant. So 205 degrees Celsius, how many significant figures? 3. What about 5.008 kilograms? 4, exactly. Okay. There's a little typo there. There should be a dot right here. There you go. A zero at the end of a decimal number is always significant. So here we have 50 liters. How many significant figures? 2 of them. And then we have 16.00 milliliters. How many significant figures? 4 of them, exactly. Remember, any zeros that are at the end of a decimal number are significant, okay? And then the easiest one is actually probably the coefficient of scientific notation, right? Those are the significant numbers. The coefficient of a scientific notation is the number that's before the x, right? So here the coefficient is 4.8. How many significant figures in 4.8? Times 10 to the 5th meters. How many significant figures? There's 2, exactly. I heard someone whisper it. Or maybe I'm just hearing that in my head. I don't know. How about 5.70 times 10 to the negative 3 grams? What? Anybody know? How many significant figures here? 3, exactly, right? You have the 0 here because it's at the end of a decimal number, and there are 3 digits there. When it gets a little complicated is when you have this rule. A 0 is not significant if it is at the beginning of a decimal number, right? So here we have 0.0004 digits. How many significant figures? 4, no, just 1, right? Because any zeros before, at the beginning, I just lost some signal here. Wait, I'm sorry, I got confused. Time out. Yes, and you're right. Whoever said 4 is correct. Because any number here, this number right here is at the beginning of the decimal number. That's the one that's not significant. Apologize for that, whoever said 4. Good job. But there are 4 significant figures because any number behind the decimal number is significant. So 10, 20, 30, and 4 for the number 4 digit. So that's 4 significant figures. And then here, how many significant figures here? 0.075. 3, exactly. So you can see that significant figures tells you how precise a scale is, right? You can jump on a scale that's just a regular old bathroom scale, and you say you weigh 150 pounds, right? But then if you jump on a scale that's a little bit more precise, it actually goes to 2 decimal points. You actually weigh 149.38 pounds, right? What would you rather be on, the scale that's more precise or the scale that's telling you you're 150 pounds? Probably the one that's more precise, right? Because it makes you weigh a little less, right? So that's the difference between having a precise scale that has a lot of significant figures, right? Or a scale that only goes to a certain number, like, for example, 150 instead of 150.38. So the more numbers you have back here, right, the more precise the scale is. The smaller something can be for you to weigh it. And then the last one is this is the tricky one right here, right? A any number used as a placeholder in a large number without a decimal point is not significant, right? So for 850,000 meters, how many significant figures? It's only got 2, and the reason why it's only got 2 is because there's no decimal point at the end, right? There's no decimal point at the end. And then for 1.25 million, right? Or 1,250,000, only those 3 right there are significant. Because again, there's no decimal right there. So that means that's only 3 significant figures. Okay? Now contrast this with something else that we talk about a lot in science, different from measured numbers, is exact numbers. Okay? Exact numbers. I'm actually I can't go back and forth like this. This is terrible with this thing in the way. Okay. We have exact numbers. So exact numbers are literally numbers that are counted, right? Not numbers that are measured, but that are counted. For example, if you have 8 donuts, literally that's 8 donuts, right? There's no measuring in that. If you counted wrong, then you counted wrong. There's no uncertainty there, okay? Then there's 2 baseballs, of course, 5 capsules, so they're all counted numbers. Another type of exact number is also are called defined quantities, defined equalities. And those are metric conversions or any kind of measurement conversions, right? 1 liter to 1,000 milliliters, 1 meter equals 100 centimeters, 1 kilogram equals 1,000 grams, right? Or in the U.S. system, what is really called the British system, right? 12 feet equals, 12 inches equals 1 foot, 1 quart equals 4 cups, 1 pound equals 16 ounces, right? And so, the definition of an exact number is a number that is not measured, okay? And they do not have a limited number of significant figures, and they do not affect significant figures in calculations. So what that means is that when you do a calculation, converting one unit of measurement to another unit of measurement, right? You'll have to use these conversion factors, but those numbers don't tell you how many significant figures there are. You'll use the actual measured values, because those are all exact numbers, okay? Those are all exact numbers. So another thing that's not listed here that's also an exact number are things like constants. Constants like the speed of light, right? Or Planck's constant. Or, for example, I have here from our last thing that we did, Avogadro's number. Remember Avogadro's number? We talked about that last time. 6.2 times 10 to the 23rd. 6.2 times 10 to the 23rd will always be that number, right? So that's also an exact number. The other thing we did too was the ideal gas constant. Ideal gas constant. And the ideal gas constant is, I don't have that memorized at all. It is 0.0821, right? And the unit there was atmospheres, liters, moles, Kelvin. Atmospheres times liters divided by moles times Kelvin. Kelvin, right? So all of those are also exact numbers too. Constants are exact numbers. Conversion factors are all exact numbers, and things like 12 dozen, right? Or sorry, 12 dozen. A dozen eggs is 12 eggs, right? Those are all significant. Exact numbers. All right. Everybody got that? Your next question is coming up. Have your phones ready. This is going to be from last time's lecture. All right, let's see how many people have responded. Oh, wow, 22 people already. Good job, guys. And everybody got that one right. Good job. What is B? Wait. What is M? Right. What is M? And M is, in fact, the slope. Good job. Everybody got that right. I wonder if I made you guys have to talk about that one. No, I did not make you guys have to talk that one. Good. So, the next thing to learn how to do is to enter significant figures in your calculator. Okay? This is important. So, make sure you have your calculator that you'll be using for class out. That TI-30 calculator or something similar, right? Do you have it? Does everybody have that? It's okay. This is being recorded, so you can always do it later, too. But say you have this calculation you have to do. 2.8 times 67.04 divided by 34.8, right? What is the first thing you need to do? Well, the first thing you need to do is multiply the 2.8 times the 67.40, right? Because you do that at the top first. Okay? After you do that at the top, you divide by 34.8. And your calculator should give you this number here, 5.422298506. And I'm telling you now that I don't want that as an answer. And when you put something like that in the Blackboard as an answer, it's not going to give you the right, it's not going to say it's right? It will not be correct. So the correct way to actually input this answer into Blackboard, because your calculator will spit out this really, really long number, right? The correct way is to figure out which number in your calculation actually has the smallest amount of significant figures. Okay? This guy here has how many significant figures? 3 of them, right? This guy here has how many significant figures? 4 of them. This guy here has how many? 2. So that means that this answer right here has to be shrunk down, truncated to what? 2 significant figures, right? So making this number 2 significant figures means that it's only going to be 5.4, and that's what you should enter into your Blackboard as an answer, right? That's what you should enter in your Blackboard as an answer. Now let me ask you this question here. What if this number here, the 2 right here, right next to the 4, instead of it being a 2, it was a 9? Then what would you enter? 5.5, exactly. You would round up everything that has a 5 or above, right? Oops, not 5.9. 5.5. Okay? Make sure you do that correctly, because on your exam and on your quizzes and on your Blackboard homework, right, you're gonna have to enter answers like that, and you have to have the right number of significant figures. There's a million different answers for everybody has a different calculator, right? That has a different number of digits that float out all the way to 12 digits or 15 digits, you know? That would just be crazy. And I'm not going to do that for you. I care about you guys, but I'm not going to do that. All right, how about this guy now? If you take 8.00 and divide that by 2.00 on your calculator, what do you get? You get 4. Try it in your calculator. If you have one out, try it. It will give you just 4. Is that the correct answer? It is not the correct answer, right? Because you, again, have to go back to how many significant figures, the lowest number of significant figures you have, right? You got to go to the lowest number of significant figures you have, count them up, and use the lowest number to tell you how many significant figures your answer should have. How many up here? 3. How many down here? 3. So that's good. So this answer should be what? Exactly, 4.00. Now these are very simple answers, but when I give you a problem, you know, like a solve a problem kind of problem, there's going to be a whole bunch of numbers in this paragraph, and you're going to have to go through, make sure you know where each number goes in the formula, and also know whether or not you need to use direct significant figures. Okay? All right. Let people write that down real quick before I move on. We did a lot of conversions there. Now let's do the conversions for temperature. Okay? Let's do temperature conversions. There we go. Not the whole thing came out for some reason. Okay. which is good because we're almost done with today's lecture. This is the last thing we're doing today. Okay? No, not the second to last thing. If I could write faster, it wouldn't be a problem. Okay, so the conversion between Fahrenheit and Celsius is different than most other measurements, right? Most other measurements, for example, you have 1 inch equals 2.54 centimeters, right? It's a one-to-one type of thing. But when you do it with, when you do it with temperature, though, the conversion is actually Fahrenheit equals 1.8 centimeters, 1.8 times Celsius plus 32. Okay, that's actually the conversion for Fahrenheit to Celsius. So the interesting thing, though, is that when I learned this, that number 1.8 was taught to me as 5 over 9, or 9 over 5, 9/5. Okay. And the reason why it's like that is because the conversion of Fahrenheit to calcium to Celsius is actually on a graph. You have to use a graph to do it. It's not a one-to-one change, right? Not a one-to-one change. So let's just take some numbers that we know for sure of what Celsius is and what Fahrenheit is. For example, body temperature is 37 degrees Celsius or 98.6 degrees Fahrenheit. So we can put that there. The bottom here will be Celsius for the x-axis. The y-axis here will be Fahrenheit, and that's where we'll put 98.6. Okay, 98.6. All right. Another temperature we know very well is the fact that water boils at 100 degrees Celsius, right? And it also boils at what? 212 degrees Fahrenheit. Okay? So we can put that here. 100 degrees Celsius. And that here, 212 degrees Fahrenheit. See, this is what it is. I need to, after every slide, I have to unplug the cord, and it starts writing fast again. So weird. So you can actually connect these 2 points, like I showed you Monday, right? You can connect these 2 points, and it makes a line, right? And it turns out that line's slope, the slope of the line, is 9 for the y and 5 for the run, right, or the x. But if you were to put 9/5 into the calculator, it would give you 1.8. Well, that's the craziest thing ever, because it turns out that this is an equation of the line, a regular old equation of the line, right? And the formula for figuring out what Fahrenheit is and Celsius is in fact the same as the y equals, y being the Fahrenheit, and then m, which is the slope, x plus b, right? Literally the same thing. So here, Celsius is the x values, right? And Fahrenheit is the y values. And your slope is there, right? And you have a y-intercept of 32 degrees. Does that make sense? There's something crazy about that. What is 32 degrees? What is that in Celsius? Does anybody know? Exactly. It's the freezing point of water. So quite literally, where if you were to extend that line out a little bit, still have Celsius down here, and you're at 0 degrees Celsius, what's the y-intercept? It's 32 degrees Fahrenheit. Crazy, right? Crazy. So that's how they actually figured out how to convert between Fahrenheit and Celsius. People did an experiment, scientists did an experiment, right? And they saw that Fahrenheit and Celsius were not changing at the same rate. when you're heating something up or melting something down or cooling something down. So they figured out that it wasn't a one-to-one ratio or a one-to-one change like most other things, right? Right? So what they did here is they figured out that it's actually a slope of 9.5. I mean, sorry, 9/5, right? For every single time, for every 5 degrees Celsius changes, Fahrenheit changes how much? 9 degrees. Make sense? And it's so much easier actually to do the Celsius to Kelvin. The reason why is because Kelvin and Celsius are both metric system. To do that, Kelvin, it's doing it again. Dagnabbit. Maybe it's because I wait too long or something. See, the newer MacBooks can do sidecar, and you don't have to have a cord. And my girlfriends can do that, and I can't do it. I'm a little bit mad. So Kelvin, I'm still messing up. So Kelvin equals the Celsius temperature plus 273. Right? No equation needed. It's as easy as that. As easy as that. Easy as that. Easy as pie, right? It's very simple to convert Celsius to Kelvin. All right. This is the last question of the day, right here. Don't worry, it's been recorded if you didn't get all that. It's not the last slide of the day, but it is the last question of the day, so don't pack up just yet. All right, everybody's logged in, and good. Most of you, the vast majority of you, picked that the 32, right, in the Fahrenheit and Celsius equation corresponds to the y-intercept, right? That's correct. It does not correspond to anything else. It does not correspond to anything else. Somebody put none of the above. So that was a trick answer. So yeah. And it's definitely not the slope. How can it be the slope? The slope is always a fraction, right? So the slope is usually a fraction. Okay. The last slide we have in our last 5 minutes is, let's put all this together and solve some kind of little problem we have here, okay? Solve a problem we have here. We have here, the Earth goes around the sun in a nearly circular orbit, nearly circular because Kepler's laws tell us it's actually an ellipse, not a circle. But for this purpose, just for this purpose only, we'll say it's a circle, right? It has a radius of 93 million miles. How many miles does the Earth travel in one revolution about the sun? Okay? So in this question, it's asking you, right, how many miles does the Earth travel in one revolution around the sun? That's literally the circumference of a circle, right? So the thing that you need for this equation, right, is the formula for circumference, right? And the formula for circumference is quite literally C for circumference equals, right, 2 pi r. Oops, not r in an exponent, just regular r. There we go. Okay, 2 pi r. So interestingly enough, this is a distance, right? That's a distance. If you were to say 2 pi r squared, that actually gives you the area of the circle. Crazy, right? Crazy. Anyway, so now that you have that, you have everything you need, okay? Because now C the circumference of the circle, which is the orbit of the moon, orbit of the Earth around the sun, right, is equal to 2 times 93 million right, times pi. What's pi? Yes. Well, it's a lot more than that. It's like 3.14159635535 something. But we'll just put 3.14. In the more nerdier circles, we try to compete to see who remembers the most digits of pi. And all you have to do is multiply all those together. Right? Oh, there's my calculator. Two times 93,123,123 times 3.14. Wow, that's a big number, guys. That's a very big number. The number is actually 5840, and then 4 more zeros. Which kind of makes sense that it's a really big number, right? 58404000. Okay, cool. Miles. All right. Is this the correct answer, though? How many significant figures? The only measured thing here is what? The radius. How many significant figures here? 2. How do we change this to 2 significant figures? There's an easier way to do it. So you could do it that way, which is correct, or you could put it in a scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, right? And you can just say 5.8 times 10 to the 8 miles. Now you don't have to write out all those numbers. Right? That makes sense? All right. That's the last slide. So coming up next week, because we don't have, I don't know if you noticed, and thank me for this because nobody else did this but me. I canceled lab next week because I didn't want to have to stagger it. Everybody else made it so that their labs had to go on Wednesday and next week, the week after. Because we have Labor Day, I canceled lab next week. So everything will be due when you get back on Wednesday on the 8th, and your fourth quiz will be on Wednesday on the 8th too. Okay? For those of you who have lab with me now, make sure you print out your thing. Did you guys all print out your labs, your density labs that I posted on Blackboard?